Yeah, thank you, Arena, and thank you for inviting me. And I'm excited to be here and talk about some of the research I've been doing with my advisor, Jurrius and Pellikaan. So as the title suggests, I'll be talking about the direct sum of q-matroids and their decomposition into irreducible components. But before I get into the work, let's give a little motivation. So q-matroids were first introduced by Crapo and Rota, by Crapo, sorry, in his PhD thesis in '64, but they were more recently reintroduced by Jurrius and Pellikaan, who find a close connection between those q-matroids and coding theory. In fact, Jurrius and Pellikaan showed that a rank metric code induces a q-matroid that captures many of the invariants of the code. And so that's why there's been a large interest in recent years on studying those q-matroids and try to find the connection between those rank metric codes and those q-matroids. And so as those q-matroids got studied pretty intensively, people noticed that there's really a lot of similar structure than classical matroids. However, this main differences really started to appear when this direct sum of q-matroids was defined. Okay, so in this talk, I will really go over the different properties of this direct sum and how they differ from the direct sum of classical matroids. So throughout the talk, I'll usually compare what is done in matroid theory to what has been done in q-matroid, so you can really see the similarities and differences. Okay, so let's first start with the definition of a q-matroid. So first, for matroids, right, we might all know that a matroid is defined over a finite set, or has a foreground set of finite set, and can be defined via a function on the collection of subsets of that finite set. And this function needs to satisfy three properties: a boundedness property, a non-decreasing property, and a submodularity property. All right. Now, q-matroids are defined in a really similar way, where now we define a rank function on the collection of subspaces of a finite dimensional vector space over Fq, where Fq is a finite field of order Q. Okay, so you can see Q as being a prime power. So we have finitely many subspaces of a finite dimensional vector space, so Fq, and for each of those subspaces, we really attribute a rank value, right? So you can think of, here I denote my vector space as E, but you can think of Fq to the n if you want to. For a certain reason, it's good to give a more abstract, define those notions on the more abstract vector spaces, but you can really think of Fq to the n, okay? So this function needs to satisfy three properties that are really analogous to the three properties of the rank function of matroid. It needs to satisfy a boundedness property, where the rank of a subspace of E will just be between 0 and the dimension of E. The function needs to satisfy a non-decreasing property. So subspace containing another one must have rank less than the rank of the bigger one. And finally, and most importantly, the function needs to satisfy some submodularity property, where now the submodularity reads as the rank of the intersection of two spaces plus the rank of the sum of those spaces must be less or equal to the sum of the ranks. And really, you can see that what we did to go from matroids to q-matroids is change the collection of subsets of a finite set by the collection of subspaces of a vector space, and then change cardinality by dimensions and union of sets by sum of spaces. Okay.
Yeah. In our space, we have a finite set of subspaces of different dimension. Yes.
Yes, you consider really all subspaces of your vector space. So the subspace of dimension 1 up to like subspace like the entire ground space.
And all subspaces pass through the origin, yes? Or we don't consider?
Yeah, it's really vector spaces as in like linear algebra. So they all contain like the identity, like I'm not sure if that answers your question.
Thank you. Yeah, I just wish to be sure that they pass through the origin, not affine.
Yeah. 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 So, I mean, this is really defined, and I mean, I'll show examples on how we arrive to q-matroids in the next slides. Okay. Okay. So, how do we get those q-matroids? Like, what is a large class of q-matroids that we can define? Well, we can define q-matroids via a matrix, right? So just like for classical matroids, where we start with a matrix, we define a matroid from that matrix as being where the ground set of that matroid will be the set 1 through n, where n is the length of our matrix, and the rank function of that matroid associated to G is the function such that for all subsets of 1 through n, I consider the rank of the submatrix consisting of the columns of G indexed by elements of A, right? And for q-matroid, it's kind of a similar process, but now we need to consider a matrix G as being a matrix over a field extension of finite degree over a ground field FQ. Okay, so G has entries in FQ to the M, and now the rank function of the q-matroid will be defined on the collection of subspaces of FQ to the M. Okay, so see how our matrix is defined over field extension, but our q-matroid now is defined over the collection of subspaces of the ground field. Okay, and so the rank of a subspace of FQ to the N just be the rank of the product between my matrix G and a matrix whose column space is equal to V. Okay, and I'll go over a little example afterwards so we can see a nice picture of what's happening here. Okay, but so one can check, and that's what Jurrius and Pellikaan showed, that this rank function really satisfy all three axiomatic properties of a rank function of a q-matroid. Okay, and so any q-matroid that arises from a matrix like that will be called representable. Okay, and this really is the analog of representability of classical matroid. And we can be more specific on the representability and say the q-matroid is FQ to the M representable if it is induced by a matrix that has entries in FQ to the M. Okay, so let's look at a little example to try to get a better understanding of how to get this q-matroid. So I can start with a matrix G defined over F2 to the 5 here. Okay, and we consider this F2 to the 5 as being really the field extension of F2. So we define our q-matroid to have for ground space F2 to the 4, because we consider our ground field to be F2. And this 4 here is really the length of my matrix. Okay. Now for any, for example, so we want to consider the rank of all subspaces of F2 to the 4. So let's choose, for example, the space generated by those two elements. And to find the rank, we take the product between G and a matrix whose column space is equal to that space. So I can just put this basis of the space as a column matrix like that, multiply G and that matrix together, and then I look at the rank of this matrix. So really what you can do is, so matroids, really you select columns of your matrix, right? And look at the ranks of that selection of columns. For q-matroid, what you're doing is selecting a FQ linear combinations of columns and then looking at the rank of that selection. Okay, so you can really see a q-matroid as looking at more dependence between the linear combinations of columns of G. Okay, and so one can check by looking at all the rank values that the rank function of this q-matroid induced by G has this nice characterization. And so you can, if you know about matroid theory, you can see that this is a uniform matroid. So in this case, it's called uniform q-matroid, where the rank of that q-matroid will be 3. Okay, and uniform q-matroids are closely related to this notion encoding theory called MRD codes, which is a nice class of codes that people like to work with in coding theory. Okay, so now that we looked at an example, hopefully it makes a little bit more sense on how to get a q-matroid from a matrix. So now let's get into more of the q-matroid theory. Okay, so just like for classical matroid, we can define different types of spaces for a q-matroid. We can, so if we start with the q-matroid, we can define the notion of independent space, where I is independent. So I is a subspace of E and is independent if the rank of I is equal to the dimension. A circuit will be a subspace of E that is minimal with respect to inclusion, and that satisfies this strict inequality property. An open space will just be a sum of circuits, and a flat F is just a space such that adding any extra one-dimensional space to it must increase the rank. Okay. And so one can see that these are really the direct analogues of definition in classical matroid theory, where we just replaced cardinality by dimension and sums and union of sets by sums of spaces, right? And in fact, it turns out that just like for classical matroid theory, one can define cryptomorphisms, so equivalent ways to define q-matroids using collections, those collections of spaces. So each of those collections of spaces fully determine the q-matroids. And if we start with the collection of such space, we can derive what the q-matroid is. So let's look at one cryptomorphism that was introduced by, that was the first cryptomorphism shown by Jurrius and Pellikaan when they introduced q-matroids. And it's a cryptomorphism based on independent spaces. So in their paper, they showed that if you start with the q-matroid and look at its collection of independent spaces, then that collection of spaces satisfy those 4 properties. Collection is non-empty, it's closed under subspaces, it satisfies this augmentation property, which you can see as kind of the analog of the augmentation property for independent sets. But it also satisfies this property I4 that says that if I take any 2 spaces, subspaces of E, and consider any 2 maximal independent spaces, I and J, that are respectively in V and W, then I can find a maximal independent space, K, that is in V plus W, and that is also contained in I plus J. So this property seems a little weird, I would say, but it is in fact necessary to show the cryptomorphism. Because if we start with any collection of spaces of a finite dimensional vector space E that satisfy those 4 properties, then that collection of spaces uniquely determines a q-matroid whose independent spaces will be precisely the collection of spaces that we started with, right? And then if you compare this to the cryptomorphism of independent sets for matroids, notice that for matroids, what we need are really those first 3 properties, right? However, for q-matroid, if you only consider collection of spaces satisfying those first 3 properties, you might not get a q-matroid out of it. And so that kind of, this cryptomorphism already give an intuition that there's additional structure to your q-matroids that you might need to consider, right? And sometimes it's a little bit more difficult to go from the theory of classical matroid to this theory of q-matroids.
I'm sorry, there is a question in the chat.
Yeah.
What is a cryptomorphism?
So cryptomorphism is just an equivalent way to define a q-matroid. For example, in our original definition a few slides ago, I used a rank function on the collection of subspaces, right? But one could define, for example, a q-matroid via this collection of independent space, where I don't necessarily need to use this rank function, right? And so that's what cryptomorphisms are. It's just really non-trivial equivalent ways to define the same object. And so that's the terminology that people have used in matroid theory, and so we stick with it. Okay, so now that we've looked at the cryptomorphism, let's get into the direct sum. Okay, and let's refresh our mind with the direct sum of classical matroid, which is not too difficult to define. So the classical of the direct sum of matroid is can be defined in the following way. So if I start with two matroids M1 and M2, they have respective ground sets S1 and S2. Then the direct sum will have for ground set the union of the original ground sets, right? And we attach the following rank function to it, where the rank of any subset of S1 union S2 will just be the rank of, so A intersect S1 in M1 plus the rank of A intersect S2 in M2. Okay. And so we can use, so there exist different ways. One can define the direct sum in different ways and use different types of class of sets of matroids to also define this direct sum. Okay. Because it is well known that, for example, the flats of the direct sum of matroids will just be the union of the flats of each component of this direct sum. And the same goes for independent set, bases, and open sets. And since all the collection of those sets separately fully determine the matroid, then one can define the direct sum using those collections of sets instead of the rank function, right? And so the one question that recently came up was, okay, can we use those definitions to really define the direct sum of q-matroids now? The problem is that none of the above definitions, if we naturally generalize to the q analog, create a well-defined q-matroid. And so we had to think differently. And so recently, Jany and Jurrius proposed the following definition for the direct sum of q-matroids. So here's how they defined it. So you start with two q-matroids with respective ground spaces E1 and E2. And your direct sum, as expected, will have for ground space the sum of those original two spaces. Okay. And now with the rank function that is defined for this q-matroid is the following, where the rank of a subspace V of E will just be the dimension of V plus the minimum of those terms over all subspaces of V. Okay, so those pi1s here are really projections from E to each of those components. And then, so what we're doing is considering the rank of those projections into the starting q-matroids that we have, right? So this definition, okay, they gave a definition. What was their idea, and why did they call that the direct sum of q-matroids, right? So the idea behind how they got this construction is the following. They started with two q-matroids, M1 and M2, and then defined intermediate q-matroids, so mi prime, which we defined for both M1 and M2. So let's look at, for example, M1 prime. How do we define that? Well, we extend the ground space E1 to a ground space on E1 plus E2. And then we define this rank function, rho 1 prime, such that, so rho 1 prime of a subspace of E1 plus E2 will just be the rank of the projection of V back into E1. Okay, so we can do the same for M2. And they call this process adding a loop space. So a loop is really a one-dimensional space that has rank 0. Is the analogous loop of matroids. And so a loop space is just a full subspace that has rank 0. And why did they call that adding a loop space? Well, if you notice in M1 prime, if you look at the rank of E2, then you project onto E1, but then you just get that the rank of E2 and My prime is 0, because the projection of E2 onto E1 will just give you the 0 space, right? And so in this M1 prime, this whole space E2 will be a loop space and have rank 0. And then using those intermediate q-matroids, then Jany and Jurrius called the direct sum the q-matroid union between M1 prime and M2 prime. The union is just an operation you can do on q-matroids that have the same ground space, and for which the rank function is precisely what the rank function of this direct sum is. Okay, so the key was really to extend this M1 and M2 to q-matroids that have the same ground space, and then unioning those q-matroids. Okay, so so that's, I guess that's a construction one can do, right? But so why is that an appropriate definition? Well, they notice that by doing the same process for classical matroids, that is extending two initial matroids or adding loop sets, I guess, and then taking the union of those intermediate matroids, actually gives back exactly the direct sum of matroids as we defined previously. Okay. And so that they considered that this works, and this is a good attempt for definition of direct sum. And we were able to confirm this intuition together, and with Jany and Jurrius as well, confirmed that by showing that this direct sum satisfied some wanting properties that we would expect from a direct sum of q-matroids. Okay, we know the direct sum of classical matroids satisfies some properties. So now we just wanted to show that the direct sum of q-matroids satisfy analogous properties. And the properties that it satisfies are, so the rank of any space of the direct sum that can be decomposed into the sum of subspaces of each component nicely breaks down into the rank of the first component V1 plus the rank of the second component V2. Okay, and so by generalizing this, we get that the rank of the direct sum of q-matroids is the sum of the ranks of each components. And now we also get that one can go from the direct sum back to the summand by taking deletion and or contraction, which I won't go over the details of how those deletion and contractions are, or restriction and contractions are for q-matroids, but they're analogous to the ones in classical matroids. And this direct sum also behaves well under a notion of duality, meaning that the dual of the direct sum of q-matroid is precisely the direct sum of the dual q-matroids. Okay, so because this tentative direct sum satisfy all those properties, we're convinced that this is the appropriate definition. Although complicated, it really feels like it is the appropriate definition for direct sum. Okay, so with this definition comes a natural question of, okay, if I start with two q-matroids, I can find the direct sum, or I can construct the direct sum from them. But then if I give you any random q-matroid, how do I decompose that q-matroid into summands, right? And so to make this question explicit, we define the notion of reducible q-matroid, which is just a q-matroid that can be written as the direct sum of small q-matroids. And if a q-matroid is not reducible, then we call it irreducible. Okay, so the explicit question we asked is, do we have a method to decompose a q-matroid into the sum of irreducible components? And second question is, okay, if we have such a method, is that decomposition into irreducible components unique? All right, there could be two different ways to break down those q-matroids. So that is a question one needs to consider. Okay, so once again, we have this question. Let's look back at what is done in classical matroid theory. So one can use the notion of connected components for classical matroid, where we can use the following relation. So we say that two elements of a matroid, so of the ground set of a matroid, are connected if there exists a circuit of that matroid that contains both elements. Okay. And this, in fact, is an equivalence relation. One can show that. And the equivalence classes under this equivalence relation are called connected components. And so those connected components are precisely the ground sets of the irreducible components of a matrix. Okay, so one given a matroid, one can use this equivalence relation to really uniquely express our matroid into the direct sum of irreducible matroid. The problem is, for q-matroid, this relation is not an equivalence relation. Okay. Okay, and this can be shown. This was shown by Sierra and Jurrius, and can be shown via the following straightforward example. I start with the q-matroid over f2 to the 3 and the following rank function, and I can easily describe what the circuits of this q-matroids is. Okay, but so these are the collection of circuits, but one note that the element 0, 1, 0 and 0, 0, 1 are both in this second circuit. Then those two elements are related because they're both in this third circuit. However, 0, 1, 0 and 1, 1, 0 are not contained in the same circuit. So this relation breaks the transitivity relation. And so we cannot define the notion of connected components on q-matroid by just using a natural analog of the classical case. So we have to think differently and try to find a different way to show that a q-matroid can be decomposable or can be decomposed into irreducible components. One unfortunate part is that in the direct sum of q-matroids, not many classes of spaces behave well under that operation. For matroids, we have that all those types of sets for the direct sum can be nicely characterized in terms of those sets of each component. For example, as I mentioned previously, the flats of the direct sum are precisely the union of flats of each summit. For q-matroid, that does not hold true. You will always have that for example, for the flats, that the sum of flats of each component will be a flat in the direct sum. However, in this direct sum process, we pick up additional flats. And so we cannot nicely write, or at least not that we know of, write those types of spaces for the direct sum in terms of each summit. Okay, so that was a little unfortunate, but fortunately, we have one last type of space that we can consider, which are the cyclic flats. Okay, so what is a cyclic flat? So given a q-matroid, I can define two types of operator. The closure operator. So if I take any subspace V of E, the closure of E will just be all the elements in E that do not increase the rank of V. So if I take V plus one-dimensional space generated by this element, I still have the rank of V. Okay. And it's easy to show that this is in fact a subspace. Okay, this closure of V for any V will be a subspace. And then the second operator we want to define is the cyclic core operator. So the cyclic core of V will consist of all elements of V such that any codimension 1 subspace of V that do not contain this element X must have rank equal to the rank of V. So see it as I take out X, right? Do I preserve the same rank? Did X contribute at all to the rank of V? Okay. And so that is your cyclic core operator. And similarly, one can show that this set is in fact a subspace. Okay. And I want to mention that the cyclic core operator was also defined by Alfano and Byrne, in which they gave the definition of cyclic core more based on lattice theoretic arguments. Okay, so they really tried to define an operator from a lattice of subspace to a lattice of subspace without considering the elements by themselves. In our proposal of the cyclic core operator, we really only consider linear algebra, so just elements of a vector space, and then show that the collection of elements we get from this operator forms a subspace. Okay. But anyways, so using those two types of operators, we define a space Z to be a cyclic flat if it is closed under both operators. So if the closure of Z is equal to Z, and if the cyclic core of Z is equal to Z. Okay. A different way to define this cyclic flat is to go via the notion of flat and open spaces. Because a subspace F of V is going to be a flat if and only if the closure of F is equal to F itself. And then an open space of a q-matroid is a space, so a space is an open space if and only if the cyclic core of that space is equal to the space itself. Okay, and so using those properties, we can also define a cyclic flat as being spaces that are both flats and open spaces. Okay, so really the intersection between the flats and open spaces. And those definitions are really natural analogues of the cyclic flats of matroids that were defined by Bonin and de Meyer in 2005. Okay, so let's look at a quick example. We start with those matrices, induce some q-matroids from those matrices, and we get the following types of spaces. Okay, so one can notice that the cyclic flats, there's really few cyclic flats for q-matroids compared to the other types of spaces. For example, take the q-matroid induced by G here. See, there's only 40 cyclic flats for more than 2,000 flats, right? So that cyclic flats really, it's a really small collection compared to other types of spaces. Okay, and so what other nice properties do the cyclic flats of q-matroids satisfy? Well, it turns out that the cyclic flats and their rank, together with their rank values, and the independent spaces fully determine each other. So if I either know the independent space of a q-matroid or the cyclic flats together with their rank value, then I can determine the other. Okay, and the equivalence goes as follows, where space I is independent if and only if the dimension of that space intersected with any cyclic flat will be less or equal to the rank of that cyclic flat chosen. So you can really see in this characterization, we need to know what the cyclic flat is, but also what its rank value is. If we take away the rank value of the cyclic flats, then the cyclic flats themselves do not fully determine the independent space. Okay, we really need to have both the cyclic flats and their rank value. But then, using the cryptomorphism of independent space that we saw at the beginning, we can immediately see that the collection of cyclic flats together with their rank values fully determine the q-matroid. So if we know the collection of cyclic flats, we know what the q-matroid is. And cyclic flats and their rank values, we know what the q-matroid is. Okay. And and this was also shown by Alfano and Byrne, where instead of going through the independent spaces, they went through the flats of the q-matroid. They showed that the flats of a q-matroid can be fully determined by the cyclic flats and their rank values, and then use the cryptomorphisms on flats to show that the cyclic flats together with their rank values fully determine the q-matroid. Okay, so there's different ways to see this fact here. But another fact we have is that one can rewrite the rank function of a q-matroid via by considering only the cyclic flats and their rank values. Okay, and so this characterization of the rank function using cyclic flats will become give us a nice idea for the direct sum. So let's look back at the direct sum of q-matroid and consider the cyclic flats of the direct sum. So what we were able to do with the cyclic flats is first, we were able to rewrite the rank function of the direct sum. Remember that the rank function of the direct sum is this lengthy, not pretty equation, okay, where we have to take a minimum over all subspaces of the space V. Now, using the cyclic flats of each component of this direct sum, we're in fact able to rewrite this rank function by considering the minimum over the spaces that are the form Z1 plus Z2, where Zi is a cyclic flat of Mi. Okay. And then by just rewriting slightly, we get the following expression for the same rank function, which, if you compare to the previous slide, seems really similar, right? And in fact, by rewriting the rank function of the direct sum of q-matroid in this way, we were able to show that the cyclic flats of the direct sum are precisely the sums of cyclic flats of each component. And so the cyclic flat seems to be really the only collection of spaces in q-matroids that behave well under this direct sum operation, right? And finding such a characterization really allowed us to dig a little deeper into this decomposition of q-matroids, right? Because we have a way to nicely characterize some spaces, namely the cyclic flats of a direct sum. Okay, let's look at an example. So these are the same matrices as before, right? And what I did is I also computed the direct sum of M1 and M2. Now notice how this direct sum here has 10 cyclic flats, which confirms our previous result, that is the number of cyclic flats of the direct sum is just the product of the number of cyclic flats of each component. But something interesting you might see from this example is that this block diagonal matrix here, the q-matroid induced by this block diagonal matrix, is not the direct sum of M1 and M2. And if you know a little bit about matroid theory, you might realize that usually this block diagonal matrix usually represents the direct sum of the two components. But from this example, we see that this is not true for q-matroids, and we'll actually talk a little bit about it afterwards, okay? But so yeah. Okay, so with this characterization of cyclic flats of direct sum in mind, let's look back at this decomposition of q-matroids, okay? So what I'll do is first define this notion of full q-matroid. So we say a q-matroid is full if both the zero space and the entire ground space are cyclic flats. You can see this as being my q-matroid has no loops and no co-loops. One tricky part is that this notion of co-loops is not well defined for q-matroid because there's not a unique way to take duality. There's not a unique way to define duality. And so this notion of dual loops, co-loops really depends on this choice of how you define what you use to define duality. So that's why instead of co-loops, we use this notion full, okay? But so if a q-matroid is not full, here's what we can already do regarding the decomposition. So we can break down our q-matroid into the direct sum of a q-matroid that has rank 0, a q-matroid that has full rank, also called a free q-matroid, and a full q-matroid. Okay, so for any q-matroid, I can decompose it using those three summons, right? And so then the cyclic flats of this n, so this n will be full, and its cyclic flats, so 0 and the entire ground space of n will be cyclic flats of n. So basically see this as breaking down all the loops of my q-matroids and then breaking down the free part of my q-matrix. So all the kind of a space that is not, so let me be more precise here. So what is this free part? So to find this free part, what we do is start with the ground space of our q-matrix E, and then take the cyclic core of E. The cyclic core of E is going to be the sum of all circuits contained, or all circuits of the q-matrix. Okay, and so with the cyclic core of E, what we do is make a choice of a complement of cyclic core of E, right? And so it can be shown that if we restrict to the space W, then the q-matroid defined on the space W will be precisely this free q-matroid. That all spaces of subspaces of W will be independent spaces, and their rank will be their dimension. Okay, and then to get this loop space, what we do is once we have the cyclic core of E, we break down the cyclic core of E as just the closure of 0, which just brings all the loops together, plus a choice of complement of this closure. Okay. And so this V here will be the ground space of N of our full q-matroid, and the closure of 0 will be the ground space of this trivial q-matroid. Okay, so we make a few choices here, mainly W and V. However, we can show that no matter what the choices we make, the direct sum will end up being equivalent. Okay. Okay. So using this decomposition already, what we need to figure out then is really how to decompose full q-matroids into irreducible components. Okay, we took out all the loops and all the co-loops away, and now we're just left with full q-matrix. Okay, so how can we use the characterization of the cyclic flats of a direct sum to find a criteria for reducibility? Okay, so this is what this result shows, is we can in fact find a criteria of reducibility via the cyclic flats together with their rank values. And we say that so a q-matroid is reducible if and only if it is either not full, so it contains loops or co-loops, or there exist non-zero cyclic flats that satisfy those three conditions. The sum of those cyclic flats have to be the entire ground space. The sum of the rank of the cyclic flats must be the rank of the q-matroid, and then all cyclic flats of the q-matroids can be written as the sum of cyclic flats contained in Z1 and Z2. Okay, and so if we find such spaces Z1 and Z2, then that satisfy those criteria, then we can rewrite our q-matroid M as the direct sum of M restricted to Z1 plus M restricted to Z2. Okay, and so using this characterization, then it becomes relatively easy to in fact show that any q-matroid can be decomposed into the direct sum of irreducible q-matroids, and each summand will be unique up to equivalence. So what was really important is just to find the fact that those cyclic flats really behave well under this direct sum operation, and then it just became kind of natural. Okay. Okay. So what can we do with this decomposition result? Well, first we can classify some irreducible components and then classify q-matroids that are defined over a relatively small vector space, right? So using this previous criteria for reducibility and irreducibility, we can show that all uniform q-matroids that have rank between 1 and n-1, where n is the dimension of the ground space, are irreducible, because the only cyclic flats of those uniform q-matroids will always be 0 in the entire space. So there's no way to break those down even more, right? And if if the rank of those uniform q-matroids are 0 or n, then the uniform q-matroid is irreducible if and only if n equal 1, because I could just always decompose. I either get a loop space or a free q-matroid where all independent space or all spaces are independent. Okay. Using this fact, then, if we want to classify all q-matroids on a three-dimensional space, we can see that the only three-dimensional or the only q-matroids defined on a three-dimensional space that are irreducible are precisely the uniform q-matroids U13 and U23. Okay, so rank 1 and rank 2. Any other q-matroids defined on a three-dimensional space must be able, we can break them down into the direct sum of smaller q-matroids, and then it becomes just easy to get the following characterization. Okay, and this characterization was also determined by Syria and Jurrius from a different approach, not using this decomposition approach. Okay, what if we want to classify larger q-matroids? Well, it already gets quite complicated for q-matroids defined over a four-dimensional vector space. What we can do is characterize some irreducible q-matroids defined over a vector space of dimension 4 that have rank 2. And to do that, we use this notion, this finite geometry notion of partial two-spreads. A partial two-spread is just a collection of spaces of dimension 2 that intersect at 0. Okay. And so from a partial two-spread, we can induce a q-matroid that will have the following rank function. Okay. And then one can show that any irreducible q-matroid with ground space dimension 4 and rank 2 is irreducible if and only if it arises from a partial two-spread like that. So we can kind of have an idea of what those irreducible q-matroids are, right? But the problem is, given two partial two-spreads, how do you know whether the induced q-matroid are equivalent or not, right? And that becomes quite tricky, because in fact we were able to find examples, an example of two partial two-spread that have the same cardinality, but for which the induced q-matroids are not equivalent. And the way that we were able to find that is that one of those q-matroid is representable, but not the other one. Except for this property, those two q-matroids have the same number of cyclic flats, same number of flats, same number of independent spaces, and etc. However, one of them is representable and arises from a matrix, the other one is not. And so it's quite interesting to see this happen. And so it seems really difficult to fully characterize the different non-equivalent q-matroids you can get that arise from those partial two-spreads. Okay. Now I want to spend a little time on the representability of the direct sum. Okay. So it's important to relate q-matroid theory to coding theory to really understand this notion of representability and figure out when a q-matroid arises from a code or from a matrix, right? And so the question that we asked ourselves is, okay, we have this direct sum operation. Is the direct sum of two representable q-matroids also representable? And if yes, can we nicely describe what that representation is, right? So for matroid theory, the answer is pretty straightforward, where if I start with two matroids that are representable over by and represented by two matrices G1 and G2, then for any choice of representation, we will have that this block diagonal matrix will represent the direct sum of matroid M1 and M2. But as we saw from our previous example, this is not true for q-matroid because we have representations of M1 and M2 given by G1 and G2. We formed a block diagonal matrix like that. However, the q-matroid induced by this block diagonal matrix is not equivalent to the direct sum of the q-matroids. Okay, and so clearly representability is much more complicated in q-matroids when considering this direct sum, and we don't really have a full grasp of it yet. Okay, but we are able to show a few results about it, and in fact show that sometimes we end up with a direct sum that is not representable. So the first kind of result we can go in describing the representation of a direct sum is the following. If I know that my direct sum is representable, so I already know it is representable, then I know that M1 and M2, so each summand, will be representable as well. Okay, and we can do that because the class of representable q-matroid is closed under deletion and contraction, and so you can get a representation from M1 and M2 if you know the representation of the direct sum. And furthermore, if we write this representation via matrix in row-reduced echelon form, then we know that the representation of M will have to be of this form, the block diagonal matrix, where G1 is a representation of M1 and G2 a representation of M2. So this is slightly different than before because first we assume that our direct sum was representable. And from this representation, we got a representation of M1 and M2. But it's if you start with representations of M1 and M2, in this case, you can now go backwards, right? Okay. And so using this, then it gives us at least kind of a starting step on figuring out whether the direct sum of representable q-matroids is also representable. So we'll see two examples. The first one, we can start with q-matroids that are representable. So here we'll consider the q-matroid to be the uniform q-matroid of rank 1. And this q-matroid is representable over fq squared. Okay. And this matrix G gives a representation where you can choose any A to be an fq square as long as it's not an fq. Yeah. The problem is, so if you take the direct sum of M, so the uniform q-matroid of rank 1 with itself, then this direct sum will be representable over a field that has has extension degree large enough. In fact, this direct sum will be representable over fq to the m if and only if the degree of extension is greater or equal to 4. Okay. And a representative matrix is given by this matrix, where here really Z has to be an element of degree at least 4, which is why we need to consider the field extension of degree greater or equal to 4 to make sure that I have such an element. The problem is if the degree of the extension is not large enough, then we may create linear dependence as we take FQ linear combinations of the columns of those matrix, right? We create more dependence, we have more dependence between those two blocks, okay, than for classical matrix. Okay. So here we have this example that shows that sometimes our direct sum becomes representable if we consider a field extension, okay? But that is not always the case. And as this example shows, we start with the q-matroid that is representable over F4. And by taking the direct sum of this q-matroid with itself, we can show that in fact this direct sum is not representable over any field extension of F2. Okay, and sometimes making this field large enough will not be sufficient to make this direct sum representable. And the idea behind this proof is to show that there exist only two representation in row reduced echelon form of this q-matroid M. And we can do that by just studying the rank function of this q-matroid M and by using some linear algebra arguments. Okay, we can show that any matrix that represents M must be of this form, and that those elements alpha satisfy those this equality, this identity. And so we can, from this identity, we know that alpha must be an element of F4. Okay, and so from that, we know that there exist only two matrices representing M, this matrix G, and the matrix G where you apply the Frobenius sum. Okay, and so because there's only two possible matrices representing M, and we know that the direct sum must be represented via a block diagonal matrix for the right choice of blocks, then we can do an exhaustive search and show that no such blocks will induce our q-matroid, our direct sum. Okay, and so this is quite surprising, especially in contrast to classical matroids. And yeah, it's quite interesting at the same time. The problem is, so we were able to like generalize some examples by using the notion of paving q-matroid and then using some notions of coding theory. However, we still don't have a good grasp on how to handle this question of representability of the direct sum. So as future work, that's, I guess, what one could try to do, right? Really try to understand when a direct sum is representable, either over a field large enough, or when is it never representable, right? And then on a different side, so with this decomposition of q-matroids, right, into irreducible component, one can start studying other invariants of q-matroid and see how those behave under this direct sum operation. For example, the characteristic polynomial of q-matroids, right? We know for classical matroid that the characteristic polynomial of a direct sum of matroids will just be the product of the characteristic polynomial of each summand. However, for q-matroid, that's not true. One can do some baby example and see pretty straightforwardly that this identity is not true. But can one find a different identity, right? This characteristic polynomial for q-matroid is also a pretty interesting object because it relates some coding theory, or like one can really get a lot of information from a coding theory perspective from that characteristic polynomial. So that becomes an interesting polynomial to really study for us and to have a better understanding of. Okay, and with that, I would like to finish, and here are a few references, and thank you very much.
Okay, thank you very much. It was a very nice introduction to a new concept. I assume there might be questions from the audience because like there are like a lot of things that could be interesting to know about this Q matroids. So any questions?
I think I might have some random questions. Okay, so wait, so I guess I'll start with a sort of random side question. Like, did you mention something about like some kind of paving q-matroid at some point?
Yeah.
Do you still expect like quote unquote most q-matroids to be paving?
That's a good question.
Okay.
I have not looked into it.
Okay.
But yeah, it's a really interesting question. I honestly have no idea, but that would be interesting to look into.
Yeah, I mean, we still don't know the other usual case, but I guess there's a quote unquote expectations. I was wondering, but anyway, okay. A couple of random questions are let's say, because we're talking about like how you can try to decompose like Q matrix, do you have any idea like if this has, and you mentioned how like, for example, we can look at like flats of the direct sum as like unions. is there any difference in like, let's say you have your ground set and how you might be able to like cover the ground set of like a matroid using flats versus like a q-matroid, like that of a q-matroid?
Yeah.
Is there a difference in like what kinds of covers are allowed, for example?
So yeah, like okay, so that cyclic flat for q-matroids, right? That will hold as well for classical matroid, where you can really decompose it in that way, right?
Right.
So one of the reasons why most of the spaces don't behave well is that as you like define your direct sum, right, you pick up additional spaces. So yeah, let's look at this. So basically, like if you look at the ground space of your direct sum, right, you have subspaces in there that can now be like decomposed into the direct sum of subspace from E1 and E2, right? And so those are the kind of spaces that will end up also being flats or independent space, right? But so the problem is that those we don't really know like how to split them up or like what kind of information they give, you know? And that's why we never end up with equalities here, because we always pick up those extra spaces that were not contained in either of the original spaces, and they cannot be written as the direct sum of spaces from the two previous one, right?
I see.
So, yeah.
All right, thanks. Okay, one last random question. So since you mentioned something at the end about matroid invariants, is there any difference in like how you would think about, say, like the independence complex of a matroid and whatever its analog for q-matroids would be?
Yeah.
Or like what kinds of properties you have there?
Yeah, so I know people have looked into the shellability of the independent complex. And they have showed that it is shellable as well for q-matroids. But then yeah, the I guess one, like because of this cryptomorphism, right? Like you have like always to consider some additional structure and make sure that things work nicely, I guess.
Right.
So it's really for those like small additional stuff that sometimes the structure you would expect just breaks down, right?
Right, yeah.
But yeah, I know, yeah, some people, I forget the authors that looked into that, but they looked at the independent complex and
okay.
try to show a little. But yeah, so that might be a nice reference to look into. Yeah.
Okay. Well, thanks.
Yeah.
Okay. Any more questions?
Yes, I want to ask about where do we use the characteristic of a field? So we can just is it important here, or we can just consider any field?
So I think so. You can consider any field in the original. I guess in the definition by Jurrius and Pellikaan, I think they kind of define it for any field and just use like degree field extensions of a certain degree to define this notion of q-matroid for any field, right? But because we're looking more into it and from a coding theory perspective, we're really interested in just finite or vector spaces over a finite field, right? And really no one has really looked into those q-matroids for like, for example, like field extension of like the reals or like complex numbers or something like that, or not. Yeah. No one. Yeah. Most of the recent papers that have come out, the q-matroids were like restricted to be over finite fields. And so for each finite field, I guess, like for the order of each finite field, like that would be a different class of q-matroids.
I'm just very curious about characteristic 0, 1, but it seems like everything goes the same.
Yeah. Well, yeah, probably. Not. We haven't really looked into the characteristic 0, but that would be interesting to see if there's any differences as you take characteristic 0 or characteristic P. Because, like, I mean, one issue would be like collection of subspaces, like won't be finite, right? And so then you might end up with some like more complicated proofs for certain statements or something like that. But
yes, for example, I also have another question. In some papers of Minkowski and Khovansky, there is also defined the notion of irreducibility of collection of subspaces, and this notion is the following: the collection of subspaces of different dimensions is linearly independent if we can choose a vector from each subspace from the collection, that this collection of vectors will be linearly independent. And like, for example, it's interesting, like does this definition is this definition
if it's
connected?
Yeah, if it fits in this context.
Yes.
Yeah. That'd be that is something I think is kind of lacking with q-matroids. Is so we know how to derive q-matroids from codes and from matrices, right? But really, at this point, I think what would be especially interesting is to find a new connection, I would say, from q-matrix to something else. For example, is there a notion of graph, right, that would kind of induce a q-matroid in that way? I think some people have looked into that with no success, but it'd be interesting to really relate this notion of q-matroid to other areas of mathematics, just like what matroids do. And I think that is at this point what's lacking a little bit. Yeah.
Thank you.
Yep. Thank you.
Okay, any more questions? Well, I guess that doesn't seem to be the case, so I'll stop the recording.